Buenas tardes todos.
Buenas tardes.
Hola.
I think I figured out the issue of why I come up multiple times.
Hello.
I think you have to log into Zoom before you enter. And if you log into Zoom, then your name shows up proper.
Okay.
I can change it as it is, but you may want to test it by trying that.
Can I?
I think,
I can
I
leave.
think that's
Okay.
it. ¿Funciona?
Creo que sí.
Excelente. Ok. Creo que tenemos casi todo. Yo una vez, dos, tres. Yeah. For those who didn't show up, basically, if you log in to Zoom before you join, your name will show up properly. If you do not log in before you join, your name will show up as me, and I can rename you. I think maybe you can rename yourselves, but that's the reason why. Okay. If you can't rename yourselves, let me say so. But yeah, I think I renamed Karina. You're Karina, right? Yes. Okay, perfect. Yeah. Any questions, doubts? I sent you guys homework. Did you receive the homework?
Yes.
Okay, some people received it, other people didn't. And Roy is still me, so it didn't work. Okay. Wonder if you registered or not. Maybe that was the thing. If you haven't registered properly, then maybe you don't have a name or something. It's confusing. Okay, so I assigned you guys some reading. Did you start the reading? Mostly, no. You can do this one.
Some part of the chapter.
Okay. Yeah.
Yeah. I also like started the chapter, but I couldn't get to read it all.
It's a decent amount of text, right? It's good for late nights. You really, you read it and you go like that. But with some coffee, maybe it's better. Okay, so the point is that the chapters and the lectures are kind of synced together, and so it would be useful if you ingested that once before we talk about it, so that the material isn't fresh, right? You've had time to digest it, and so when you see it again, if you have questions or doubts, you can ask the questions, right? If you don't do the reading and it just comes at you, you're just going to gloss over and not have time to think about it. And so that's the point. Carlos, okay, so maybe you didn't join when we were talking about it the first time, but let me share my screen. Yes, yeah. Basically, there's a link which you can get to from the Canvas page. My Canvas looks much more chaotic than your Canvas, I guess. Come on, you can do it. There we go. So in Procesos, and so the home, there's a link here. And if you go to the link, it's here. So all of the information is there rather than the canvas, because I hate canvas. So if you click on this, that's a PDF. If you click on this, that's a PDF. And those are PDFs of the lecture. I may tweak things a little bit. For instance, I realized that the font was terrible, so I'm starting to redo the font as I go through it, so that the news look like news and not V's, like velocity. So yeah, but I haven't updated this for that yet. I was just doing it in the last half hour. So this is cool. Okay, is that clear, Carlos? See, no? Chat, yes. Okay. All right, so we were talking about brightness, flux, all that good stuff, right? So let me put this over there. And we had three different quantities, really. We had the luminosity, we had the flux, and we had the specific intensity, brightness, specific brightness. There are lots of different words for it, depending on who you're talking about. And also the luminosity is luminosity per hertz, or flux per hertz, or if you integrate over a band, then it's a sort of either a luminosity or flux in a band, or if you do from 0 to infinity, the bolometric luminosity. That should all be sort of familiar to you. So the difference between brightness and flux, as we had talked about before, is more or less this solid angle. And if we think about the flux density in MKS units is watts per meter squared per hertz. Right? And in general, the quantities of flux in watts per meter squared per hertz are really tiny, particularly if you're working in the lower frequencies or long wavelengths, radio band. And so the radio astronomers, because they didn't want to carry around 10 to the minus 26 everywhere, they renamed their units as Janskys. And so they talked about things in terms of, oh, this radio source is 1 Jansky. Right, much easier than 10 to the minus 26 watts per meter squared per hertz. So you'll see that if you study radio astronomy, you'll see that quite a lot, this Jansky term, but this is the conversion. And if you convert these guys to CGS units, there's a 10 to the minus 7 here, there's a 10 to the 4 here. This converts, and so you end up with a 10 to the minus 3 difference. Now, as radio astronomy got more and more sensitive, we actually had sources that had much fainter fluxes, so 10 to the minus 3 Jansky or 10 to the minus 6 now, and those are millijansky sources or microjansky sources. Right? So there's lots of different nomenclature around. I'll bring up a couple more examples in a few slides. So basically, this surface brightness compared to the flux density is not an independent quantity, depends on the distance. And so because if we integrate over the solid angle, this is proportional to 1 over d squared, right? So the flux is proportional to 1 over d squared. This is our famous inverse square law. And this is just sort of a picture of this sort of the situation. So the specific intensity, the brightness is intrinsic, the flux isn't. We can also think about the spectral luminosity. And this is the per hertz luminosity. And this would then be the total power per unit bandwidth. So for some frequency interval. And so this would be basically the total power per unit bandwidth radiated at some frequency nu. And so in MKS units, this is watts per hertz. And so if we think about a sphere of radius r, it's going to have a surface area of 4 pi squared, 4 pi r squared. And so we can kind of use our inverse square law, right? So the luminosity You've learned before that if you have some flux and you know the distance, you can figure out what the total luminosity is, right? And it's just simply 4 pi d squared times flux equals luminosity. And so this is the same thing, but just per unit of frequency, right? And so it looks like this or like that. And those things hold. So this spectral luminosity.
I have a question about that equation, because the second one, the one with the flux, we saw before that flux was the luminosity divided by 4p, the radius, the radius 2 times.
Squared.
And when I saw the class, shouldn't be only the flux, or do we, how do we keep having that 4p? How doesn't it like disappear? I think that I may have compared to weird things.
Well, so just, what is the surface area of a sphere?
4b d 2 times.
Yeah.
Oh, that's all. Okay.
That's all.
Okay.
Yeah.
Okay.
And so the thing is, when you have an isotropic source, right, you have a certain amount of radiation which is leaving it per second. That's the luminosity. And so depending on where you put this sphere, you will have a certain amount of radiation that you get per unit centimeter squared or per unit meter squared, which is what the flux is, right? So the flux, all that is taking a unit in that sphere. And so if you're closer, that unit ends up subtending a larger solid angle of the sphere, and therefore it's higher. Right?
Thanks.
Yeah. Okay. So this spectral luminosity, again, it doesn't depend on distance. So it's also an intrinsic quantity. We can estimate the bolometric luminosity or a band luminosity by doing this integration, right? Which is what we had discussed at the start of the last class. So to sort of prove this, we can think of the following sort of example. So we have an object here which has a radius r. So let's say this is some source, and then we have emission which is going on from this sphere here. So this sphere is has a uniform brightness. It's, for all intents and purposes, it's the surface of the sun or a surface of a star or whatever. So it has a radius r, and it's emitting on its surface with some temperature, and so the emission is more or less uniform. And then we have an observer or some point, where we're going to measure the amount of radiation coming from the source. And so this thing has a uniform brightness, I nu, and we want to measure the flux out here at P. And P is a distance r away from the center of the source. For our purposes, this is going to be pretty large compared to this. So that this sphere doesn't take a large fraction of the sky, because then light isn't coming in parallel. So we can say, okay, the flux is equal to this specific intensity times the solid angle. And we want to integrate over all of these angles. And so we have this small solid angle. We have the fact that it's related to cosine theta as well. So the intensity depends on this theta. And so we can substitute in this as more or less just being sine pi d theta, sorry, sine theta d theta. And then we want to integrate out to some critical angle, because after that, there's no source, right? So the critical angle is more or less this here, or well, it's actually this here. Here. So that's the critical angle. And we want to integrate from the center to the critical angle, and then 2 pi will integrate the other sort of angle phi here. Yeah, we have a phi back here. So we can notice that of course sine theta is simply given by this radius and this radius, right? So we can plug that in. And then we can also use this sort of mathematical formalism that if we integrate from 0 to some value of this quantity, this integral ends up just being sine squared of this angle. We could do the math, but this is easier to just convert it. And so what we end up getting is that this integral ends up being equal to this. And so it's proportional to 1 over r squared, right? So we recover our inverse square law. And really the entire premise of the inverse square law is simply a consequence of the fact that the solid angle of objects decreases as you move away from them. That is really all it is. And so what's interesting is at the surface, right, when little r equals r, in theory, this equals 1, and then we have that the flux is equal to the intensity times pi. And so this is also sort of used in some cases. Okay, so that's hopefully relatively clear. These are basics that I think we may have seen before. Right? So just to give you an example of spectral brightness, flux density, spectral luminosity, let's look at the sun. And so the sun has a black body temperature of about 5,800. At least that's what we observe. And so we want to look at what the intensity is at a very, very low frequency in the radio band, so 10 gigahertz. And so we can use our lovely Planck formula here, and we'll get to this a little bit more in depth later. But we can also, this formula, it is sort of a power law on the Rayleigh-Jeans tail. It has a peak, and then it has the wean sort of drop off. And we're going to be, because we're at 10 gigahertz, we're clearly in the Rayleigh-Jeans regime, and you can see that just by evaluating this ratio here. And so if we plug in our nice values for this, we end up with something which is well below 1. And so this thing can be expanded because it's a small number, and then we would end up with the Rayleigh-Jeans approximation, which is that this intensity is simply equal to a couple of parameters, and then we've expanded this thing. And so the temperature comes out here. And so we can estimate this. It's simply the Rayleigh-Jeans tail is proportional to the temperature and to the frequency squared and a few constants, right? So this black body is in intensity, and so it's equal to our intensity. And so the spectral brightness is simply just plugging in these values here into this. So we can plug them in, and we end up with some number, which doesn't mean a whole lot, but that's the intensity that we would see at 10 gigahertz. Is that pretty clear so far? Okay.
I have a question from the previous exercise, but only for corroboration, I mean, because it's valid if we assume that P is a source and the cascade, I mean the surface of the sphere, is our detector, and it's valid to construct construct mathematically the flux, the spectral flux, as in the inverse situation.
Yeah. So for here, what we considered was simply a unit area, right? But that unit area could be, for us, that was a detector, but it could have been an emitter. And then this thing here, we could consider our detector. And so by the principles that we talked about on the first lecture, you could invert them, and they should be the same.
Okay. Okay.
It's a little bit tricky here because the unit detector isn't, I mean, it's kind of hidden in the flux, right? Because it's just per centimeter squared or per meter squared.
Yeah, it's because, well, in some cases, I think that is easier to imagine the detector as an area, and you can imagine the normal vector of the detector normal to the surface. So for that reason, it's a little think that
Exactly.
is
So it's
Yes.
simplified to some extent, right? Because yeah, we don't have the angles for both of them or anything like that. So it's been kind of homogenized to, so
Yeah.
it's not as complex, more or less.
okay. Thank
Yeah.
you.
Okay. Okay, so we have our specific intensity, right? We can calculate the flux. And so we have this specific intensity. We also notice that here we had units of ergs per centimeter squared per steradian per second divided by hertz. And so this is a little bit cumbersome. If you want to convert it to MKS units, you can note that we have this conversion, we have this conversion. And so you could, if you ended up converting it, so you plug in all of these values into the formula here, and you end up with something which is different by 10 to the minus 3, which is simple. Okay. And of course, noting that this property is it's intrinsic. It's an intrinsic property of the sun. It doesn't depend on the observer's distance because it's the intensity. So I should note at this point, I had mentioned before that typically radio astronomers tend to use MKS units because in the early days, radio astronomers were mostly engineers and they had embraced MKS units. Optical astronomers have often used CGS units. And so you should be comfortable going back and forth between them because you will be thrown all sorts of stuff. And so there's a nice package within Python which allows you to kind of do this automatically. I have not mastered that package, but I encourage all of you to use it liberally if you can. For me, it ends up being a little bit complex, and I always have units, and then I want something, and I have to divide by the unit in order to get something that's not a unit anymore. It confuses me a little bit, but I think if you start using it from scratch, it's more natural. The other thing to sort of mention is that if you go to very high energies, their astronomers tend to use energy equivalents. And so they will talk about things like electron volt. And so they, sometimes we'll use CGS units, sometimes we use EV. So we'll say something has 10 EV, and it's sort of an equivalent of some energy. You can also, astronomers will also sometimes use KeV, kiloelectron electron volts or mega electron volts. And, you can think about this in terms of sort of relative to the rest energy of a proton or electron, right? So when you get to that sort of level, again, they're very cumbersome units. In terms of frequencies, we're talking about 10 to the 18, 10 to the 20 hertz. And so maybe it's easier to talk about things in terms of an equivalent energy rather than the frequency. So that's all. Okay, so we can then calculate the flux density. And so we'll calculate it at Earth. And so we have the radius of the sun, which is roughly 7 times 10 to the 10 in centimeters, 6.96 something something. We know the distance from the sun to the Earth, which is 1 astronomical unit, or roughly 1.5 times 10 to the 13 centimeters. And so we can figure out what the angle is on the sky by taking this ratio, taking the inverse sine of it. And so it's a very, very tiny fraction of a radian. And we can then integrate over this small portion of a radian, this half a degree, and we have the intensity, the specific intensity, right? So we can just plug these values in, and we can get out a flux density for the sun. Recall that again, we're integrating to the radius of the sun, which is now theta solar as opposed to theta critical. And then we're integrating from 0 to 2 pi, and we integrate this thing here. And so again, we can kind of plug all this in and use some mathematical tricks here to end up getting a value for this flux density. We can plug those values in. So if we end up doing this integral, we end up with, here was our value for theta, with this small theta, because it's small, we can expand the sign. And so basically sine theta equals roughly theta for small values of theta. And so we have more or less this. We plug this in and we end up with some value. It's very, very tiny, 10 to the minus 20 in MKS units. If we convert to Janskys, then it's super bright. And this is why radio astronomers did that. Most radio sources tend to be in the early days, they tended to be sort of in the 10 to 100 Jansky range. So it was very convenient. This, of course, is not a property of the sun because this depends on our distance. And if we were further away, it would be lower. If we were closer, it would be higher. Okay, then we can, of course, calculate the luminosity, again, but just by multiplying by 4 pi r squared. And so here's our 4 pi r squared, and we end up with a spectral luminosity, which is a few times 10 to the 10 CGS units. All pretty simple, hopefully. Okay, so another quantity that will come up, it's maybe not quite as commonly used as luminosity or flux density or intensity, specific intensity, is the energy density. And so here we'll call energy density U. And so it's a function of frequency again. And this is the amount of energy that is in some volume element, dV. And so if you were to integrate over this volume, you would get some energy. And so this energy here, this infinitesimal energy, is equivalent to the energy density times the volume times the solid angle times this sort of frequency element. And of course, we can note that in some element or some volume element, if we were talking about radiation, the radiation is moving at the speed of light. And so the passage of that will be related to the speed of light times the delta time that we have, right? And so you'll have, light will move a certain distance in this dt, and that distance will be related to that. And then we have a certain area with which it's sort of moving through. And so if we break that down, then this small amount of energy is related to these functions. And of course, we can sort of replace some of these functions with other ones. And so it turns out that if you do that, you end up that the energy density is simply the specific intensity divided by C. And so a sort of convenient way of going between these is that the energy density is just the specific intensity divided by C. What does that mean? Well, it means that specific intensity is a conserved quantity. It's an intrinsic quantity. And so the energy density is also going to be a conserved quantity because this is simply a constant. Okay. So if we had the total energy density, what we would then do would be to integrate over the entire solid angle. So 4 pi steradian. And if we did that, then effectively what we were doing would be integrating the specific intensity over the entire solid angle. The C just moves out here. And if we do this, we can, this quantity here, the specific intensity, if you integrate it over all solid angles, is just the mean intensity. And so this is sort of just a definition, but the mean intensity ends up being this integral, and it's normalized by 4 pi. If the field is isotropic, then these two things are equal, right? Because this is normalized by 4 pi. But if they're not isotropic, if there's emission to one side versus the other, then this would not hold. And so, in essence, this, if we want to integrate this over frequency, we end up getting the total energy density, and this is simply integrating from 0 to infinite frequencies of this quantity here, because we've already integrated over solid. But you could play various games with that. Okay, so how would we actually go? How would we use U, for instance? Because it's a little bit less intuitive for us. And so we can think about how we would convert from a luminosity, which we're very familiar with and comfortable with, to this energy density. And we'll do 3 different scenarios to give you some idea of how to do this. And so one possibility is if we're actually outside the source at a large distance, then this calculation is relatively simple. If we're inside the source, then it really depends on the distribution of the source, how the source is emitting light. And that will dictate what the energy density is. And so we'll have second, so we'll calculate this for a large distance away from the source. And then if we're inside the source, whether it's emitting uniformly throughout the source or from a shell. And those would give different answers, of course. And so if we're outside, then we can consider a shell with a surface 4 pi d squared. So right here, and then has some sort of height or thickness of this shell, which is going to just be the speed of light times dt. And so then the volume of this shell will simply be the combination of these two, right? If provided that d is significantly large, and so we can just use this as a convenience factor. We have a time, so in some dt of time, we're going to be able to emit some energy, which is related to the luminosity times this time. Right, so if we have some time interval, we have some luminosity, which is energy per second. We multiply times this interval time, we get energy. And so this energy is going to be contained within this spherical shell. And so we can calculate an energy density this way. So the energy density is simply this sort of small parcel of energy divided by this small parcel of volume, and this within the equivalent to luminosity divided by luminosity times time, and then this volume element will be this, and of course the times cancel out, and so you end up with something that looks like this. So luminosity divided by 4 pi d squared times c. Right. Everyone follow? Hopefully. So that would be the energy density that we would acquire, that would be radiated from, that would pass through the shell. Okay. This, of course, will be different depending on how, it's a function of d for one. But because this source is down here and we're far away, if we move d, we're just making a smaller sphere, and this should hold. Now, if we end up being inside the sphere, then things kind of depend on the actual physics a lot. If we assume that this source is optically thin and homogeneous and uniform, so we have just a uniform emission throughout the sphere, then in this case, the energy density here just depends on what we call the mean escape time from the source. And so to give you a sort of example here, we have a fixed luminosity. And so we have basically that if we have this luminosity, Actually, I need to think about this. So for given fixed luminosity, we would end up having a longer, basically the longer the escape time, the larger the energy density. So if we increase the escape time for a given fixed luminosity, we would increase the energy. Simply increase the time, multiplied by the luminosity, you get higher energy. And so the more this, we can think of this as if for some reason the photons are delayed, they don't go as c, but they go as something slower than c, or that there's this amount of time needed to escape the source, then you will accumulate energy within this. And this is sort of useful when when you start thinking about the fact that the sun emits most of its energy in the center, and it takes 10,000 years for that light to escape, even though the sun's radius is only 7 times 10 to the 7 times 10 to the 10 centimeters. And so the speed of divide that by the speed of light, you get a time, and that should be of order 1 second. And so there's something that delays that energy from getting out. And so what that means is that the energy is accumulating, and you have a higher energy density within the source. So this is kind of what I'm getting at with this. And so this energy density is proportional to the luminosity, the volume, and then the escape time. Right. And so again, you can, for some source size C, if this thing is optically thin, then the escape time ends up just being the radius of the source divided by C. And if there's other physics going on, then this wouldn't hold, and this would not hold. Okay, now, of course, this particular equation only holds for a photon that's emitted at the center, and then it has this, it travels the radius, and the escape time is then R divided by C. But if this thing is uniform, then this will depend on which direction it goes, where it actually was emitted, all that. And so we can do this integral. And so, if a photon, for instance, is created at the border, half the time it's going to just leave with an escape time of 0, and the other time, the other half will go through the source and it will have a non-zero escape time. And so, roughly speaking, the escape time would be half of this. Or rather, half would escape immediately, half would have to pass almost 2R to get through, not quite. And so if you do this proper integral, you end up with something which is kind of proportional to about 3/2 this. And so for a uniform sphere, you end up with an energy density which looks something like this, just to give you an idea. But the point here is that this ends up being a little bit higher by a factor of 9/4 from the thing that we estimated here. Right. And so it's a little bit different. If we were to set D equals to R. Okay. So this, of course, as I mentioned, is only for an optically thin source. Another sort of visual example we can do is if the source is completely empty inside, and we're inside, and we see it as a sphere more or less radiating all around us. And so if it's a uniformly emitting shell, then if we're more inside of it, really all that we end up seeing is something where the emission is coming from a distance more or less R. And if we move a little bit, then we'll have some that's coming more intensely on one side than the other. But roughly speaking, if we're kind of sitting at the center, the energy density will be proportional to the first equation that we had. But now we're inside. So it's basically a specialized case of the first case. This is just to give you some pictures of what this energy density would kind of mean. Is this clear? Let's see. Time, that's bad. Okay, so we can then, once we have a sort of solid definition of the quantities that we're talking about, then we can start to think about the just simple radiation transfer. And so we have a source of emission and it emits the light, and then the light travels along throughout space. If that space is empty, nothing necessarily happens. If you're in cosmic expansion, something happens, but for now, we're not in cosmic expansion. We're not doing anything with that. So it just travels along and nothing happens. The intensity is conserved along its path. And so another way to state that is simply that the change in intensity as a function of the change in distance or the change in its path, that is zero. Nothing happens to it, right? The intensity is constant. So if we take the derivative with respect to its path, it's zero. Yeah. And so the trick happens is, okay, space isn't actually empty. It has stuff in it. And that stuff can interact with light in a bunch of different ways, which, you know, we kind of listed many of the ways it could interact in the first class. And so imagine that we have a source and it emits light, and there's some material here, and then we have our detector at the end of that, right? And so what happens in between this and this, and how does it affect this? This is what radiation transfer is all about. This is a very classical macroscopic model of the interaction between radiation and light. But we can use this to kind of develop an understanding of how we're going to treat various situations. So we have some light that's going in, and then depending on the amount of material here, you're going to have, as the distance or the path increases, the possibility for interaction increases, right? If this density is uniform as a function of the path length, then every infinitesimal portion ds that this passes through, there's a probability of an interaction. And we can think about the interaction as an optical depth, which we will call tau. And so if something is optically thin, it means the probability of interaction is very low. If something is optically thick, it means the probability is basically 1 or higher. And so as you increase this path, you will increase this. And this increases in this direction, and S increases in this direction. So as this photon first gets in, it's a small amount of material, and so tau is relatively low. But as we increase the amount of S, this tau is high here and low here. So as this light is traveling through this material, the probability of interaction increases, is kind of how to think about it. Okay. So then we can think about what happens to this light. Let's say we have a beam of photons or light particles, and the medium absorbs them, right? So there's some probability that a dust grain, for instance, is able to absorb a photon, and it disappears, vanishes from sight. And there's a probability of this happening as a function of frequency. One thing we want to be careful about is almost every process is a function of frequency. And this is why we write things in terms of frequency for practically everything. Because the processes are not very necessarily smooth. And so if we do infinitesimal frequencies, we can piecewise integrate this, and it becomes easier. Okay, so we have some probability that will be absorbed, And we have a thin slab of this material, which is ds. And so this probability is proportional to ds times something. And this something is a frequency-dependent constant. And we call this the linear absorption coefficient. Right? So it's related. So if you have a certain amount of material, depending on what that material is, you'll have a certain probability of absorbing a photon. Yeah. So that's this thing. And this depends on the microscopic properties of the object. So if this thing had a value of 1 meter squared, and yeah, so this linear absorption coefficient, basically it has a dimension which is inverse length. And so if it had a value of 1 meter per meter squared, what that would mean is that over some small distance, delta S, this thing has to be less than the inverse of this. And so if we're talking about a delta S of 10 to the minus 3, for example, here, then this quantity would be relatively small. And so multiplying these together, you have a probability of 10 to the minus 3. So 1 in 1,000 photons will be absorbed. So it's not made. Right? But as you increase delta S, right, as delta S becomes equivalent to this, then the probability becomes 1. Pretty straightforward. Okay, so why do we consider layers rather than the whole absorber at a time? And this is mainly because this linear absorption coefficient, basically, if this layer is thin enough, this probability is infinitesimal, and this probability of an absorption layer will increase linearly with the thickness. If we have a thick layer, this is enough to absorb a significant amount of photons. And so what ends up happening is you end up having fewer photons absorbed near the end, the far end, than the near end. And you end up having a disproportionality because you are taking too large of a chunk and something is changing to, the processes are being affected by this. Right? This side of the material isn't seeing the same number of photons as this side, because the probability becomes close to 1. And so you want to have a small enough thickness so that you can evaluate the incoming number of photons as being uniform on one side to the other of this small element ds. And so what ends up happening is that if you take too large a thickness, the probability of absorption increases nonlinear with the thickness, more or less. So this particular macroscopic model is nice because it doesn't depend on the microphysics, the microscopic physical processes by which a photon is actually absorbed. Right? You hide all of that in kappa, this linear absorption coefficient. So all the atomic physics, all that good stuff, that's all in here somewhere. So if you have something like the ideal gas law, basically the ideal gas law works on a macroscopic level without any consideration of what actually it is for one atom to interact with the other atom, which is a microscopic process, right? Or one molecule to interact with one molecule. So we can also rewrite this kappa in terms of a number of particles and some cross-section. And so again, this is a macroscopic concept, but we can say that the probability of a photon interacting with this chunk of space is proportional to the number of atoms that are in that space. Right? And so in this way, then we kind of link the macroscopic to the microscopic, which is the interaction of one photon with one atom. And there's a lot that could go into this, but for now we'll keep it relatively simple. Okay, so we have our initial equation, which was the change in intensity divided by the change in path length was 0. It was constant because there was nothing there. However, now we have a process which is that some of the photons are absorbed, right? And so the change in intensity, the specific intensity with respect to the total intensity, is related to our kappa and the path length, or this probability, right? This is for absorption processes. And if we integrate this over both sides, we can basically integrate this equation here, well, this sort of scenario where we have some path length input and some path length output. You can imagine this being a cloud of gas, right? So we have empty space, and we have a cloud of gas, and then we have more empty space. And so we're just integrating over this chunk here. So integrating between these two, we integrate this thing, and that really means integrating this. And so we integrate that, and what ends up happening is that we end up having, if we integrate this thing, we have the natural log of the intensity over evaluated at S in and S out. And if we integrate this thing, we have more or less that we'll keep this for the second, but this quantity here, we can end up considering this to be a dimensionless quantity because this is the path length and this is inverse of path length. And so this is dimensionless. And so we call this integral the opacity, right, the optical depth. And so coming back to our schematic here, this tau is inversely related to S. So as S increases, the tau will increase this way. And this is just in terms of the sign of things. So if we have this natural log and we take this integral, what we can kind of evaluate this as is we can multiply or take the exponential of this, the exponential of this, and so we just have the intensity in and the intensity out. And so the intensity on the far side of this cloud is the intensity in multiplied by some exponential of this integral, or an exponential of the optical depth. And so we end up with a relation where the input and the output intensity is proportional to the exponent of the probability of an interaction, right, of the integral of the probability of an interaction, which should be pretty straightforward. Right? Generally, if the photons move in, there's some probability of it interacting. If it interacts, it takes away a photon. Right? So if this is very, very low, if this is 0, then this just ends up being 1. Right? And input equals output. If this is high, and here's where the negative comes in, then this thing ends up being very, very small. And multiplying a small number times the input means the output is very small. So everything gets absorbed. So the higher the probability, the higher the chance of absorbing photons, and this being low. Okay. So then we can make this a little more complex. We have our initial source, we have some absorption process, but what if we have a process which is emitting photons along this path length as well? And just to give you an example of, we absorb a photon, a dust particle absorbs the photon, and it re-radiates it in the infrared, right? And so that process is dependent on how many photons are absorbed, right? And so it makes sense to do this emission as a function of the path length, because the amount of photons that are absorbed is dependent on the path length too. So, but we can do this in generic terms. And so we have some emission. And so the emission, we will think about this as this medium of particles can emit photons, and by some microscopic process that's unspecified at the moment. And so if we have some small volume, and we can divide the small volume into our path length and some area, right? Then there'll be a probability per unit time over which these atoms might emit a photon with some frequency nu. And it'll be emitted into a solid angle of delta omega. And these are directly proportional to the volume, to the volume we have and this solid angle, the probability of emitting a photon. So this probability of emission is proportional to the solid angle, it's proportional to the volume. And so we can define something called an emission coefficient, which is the change in intensity as a function of this small portion of the path length. But now this is the amount of radiation that is increasing, right? The emission, it's being input into the system. And so if we ignore absorption and we ignore our initial source and we just have some medium that's emitting, then as we integrate over S, we will have some intensity that is being emitted. And so this is what's meant by the emissivity coefficient or emission coefficient. This thing here has dimensions, which are the dimensions of intensity divided by distance, right? And so in MKS units, it would look like this. So there's this extra per meter here. And now we can add them both together. And so the change in the intensity as a function of the path length is related to our absorption, which depends on the number of incoming photons, right? So it depends on this, and the emissivity or the emission coefficient. And again, this to see this portion of it, let's go back, right? So we had this with this, and all we're doing is rearranging the variables. So we're moving the ds over here and the I over here, right? And so in this way, we can calculate, we can integrate over S and find the total change in intensity from absorption processes and emission processes. Voila. Okay, so we haven't discussed at all the microphysics here. These are just simple coefficients that we can plug in whatever microphysics we want. It could be a line emission, it could be black body emission, it could be synchrotron, whatever. Okay, so another thing that's sort of interesting here is that these don't have to be in any kind of equilibrium at all, right? So at the moment, they're completely independent of thermodynamic equilibrium, or TE. Now, if matter is in thermodynamic equilibrium, what that means is that the matter and radiation are coupled together, more or less. And so if something's in thermal equilibrium, then you'll have equilibrium radiation at some temperature T, which is isotropic and has a black body spectrum. And so one specific case would be for an object, which is a black body, to absorb incoming radiation, and it will heat up, right, to some temperature, and then it will emit as a black body with black body radiation. And so you can solve this equation for that specific case, right? But this thing is more general than that. One source of black body radiation, sort of a mental construct, is, let's say we have a cavity and it has opaque walls, and there's a small hole in which radiation is coming in. And so the intensity and the spectrum of this radiation doesn't really matter, but it comes in, and this material, whether it be wood, concrete, whatever, generally this will come in, and you have some absorbing material inside the cavity. This could be gas, dust, water, whatever. And so after some particular time of mixing the radiation that's coming in and this material which is absorbing that radiation, those two things will come into equilibrium with each other. And so generally speaking, if you have thermal radiation coming from the cavity, basically this radiation will only depend on the temperature, and it will end up being more or less independent of any of the material that make up the cavity walls or make up the contents. So all we see in terms of the radiation coming out is something close to a black body, if this material is a pure radiator. Most materials aren't necessarily pure radiators, and so you don't get pure black body coming out. But for the thought experiment, that's what we'll have. And so Kirchhoff actually proved this statement by the following sort of mental construct here. And so let's say we have some object which is in equilibrium, and so the radiation here is in equilibrium with the material, the temperature of the material, and everything. And so it emits a black body coming out here. So if we put two of these boxes together and we close the hole with a filter that passes light but doesn't pass any material. So, and then these boxes are there's no transfer of energy between them from kinetic means, just from light. So the only way to transfer energy here is from light. And so this thought experiment is you take two cavities, they're both in thermodynamic equilibrium, but at different temperatures. And you let the light pass through them. And so after some time, enough light will pass through both ways that these two cavities will come into thermodynamic equilibrium at they basically have the same temperature if you give it enough time. Because this thing, if it's hotter, will radiate more energy will go through this one, will be absorbed by this material, which will then give it more energy. And essentially at some point, these things will have a transfer which is equal, meaning they're in equilibrium. And so, this sort of process, if you cool one or heat one or the other, this ends up violating the second law of thermodynamics here, because these two temperatures are if these two cavities are at different temperatures, we would end up being able to sort of use this as some sort of heat engine and derive energy from it, and that by conservation laws that shouldn't happen. So more or less these things should come at equilibrium, and that kind of should be it. Okay, so we can think of our radiation transfer in this particular way. Right? And so let's think about it. We have a system which is in full thermodynamic equilibrium at some temperature T. And so in this case, the energy per time ends up being 0. So the intensity is constant. The intensity is equal to the black body. And so if this is the case, right, if we have a closed system that's in thermodynamic equilibrium and has it's a black body, then what that means is that the absorption and the emission are balanced. Right? And so we can plug in our functions for that. And so we have here, the Planck law is our intensity. And so we have our Planck law here, that's the input. And then we have some medium, which is absorbing it. And then we have our emission process, which could be something else potentially. But because this system is closed, right, we can put this on the other side and we can divide by this. And so what we end up getting is that the emissivity divided by the linear absorption coefficient, this quantity here, is equal to the Planck law. And this is more or less saying that, you know, you're equating the emission and the absorption processes. That combination together is generating your Planck law, regardless of the microphysics that goes on. Now, this argument is, what this means is, of course, that, you know, this is a function of temperature, and so both of these end up having to be a function of temperature. If they're, we don't know what the processes are, but they should end up being a function of temperature. So this argument here is clearly independent of a cavity shape or, you know, the specifics of this particular process. And so one of the outcomes of Kirchhoff's law is basically that black-body radiation must be isotropic, sort of by definition, because it doesn't matter what the shape of this is. It should be the case that it will end up being an equilibrium. Okay. So this, you know, Kirchhoff's law was originally sort of devised for thermodynamic equilibrium, but actually we can apply it to non-equilibrium cases. And so, right, we don't necessarily need to plug in the Planck law here, but we could keep our intensity. And so then we wouldn't necessarily be in pure thermodynamic equilibrium, but we might have processes whereby this change is zero still, in which case this still holds, or this process isn't zero, but we can still apply it. So this is sort of the beauty of this formalism. So if we have an emitting material and it's in thermodynamic equilibrium, it has a well-defined temperature. The radiation field that it's interacting with does not need to be in equilibrium. And so if this is the case, so you have a material which is in equilibrium, but the radiation field is out of equilibrium with it, well, we call this situation local thermodynamic equilibrium, or LTE. And a good example of this is the Earth's atmosphere. Right? So the Earth's atmosphere is absorbing light from the sun, it's reflecting light from the sun. And so when it ends up coming into equilibrium with itself, it roughly has a temperature of 300 Kelvin, right? 27 C or so. Obviously, the light is coming from a source which has a thermodynamic or a thermal equilibrium, a black body temperature of 5,800, right? And so this is what's meant by local thermodynamic equilibrium. The atmosphere is being heated up by that light, but it's in equilibrium with the input radiation field, but the two things are not necessarily coming from the same source. Okay, so Kirchhoff's law obviously applies in LTE as well as in thermodynamic equilibrium. And one way of showing this would be to take the black body the equation, this Planck law. You know, this is a function of temperature only, and it shouldn't matter in whatever the properties of the radiation absorbing material are. Whereas both of these depend intensely on the material, the properties of the cavity, etc. And so they also depend on the temperature of the material. Right? And they don't necessarily depend on the radiation field or its spectrum. Okay. Any questions so far?
I have a question, but it's a little from the information before. For example, when we have dust and there is absorption by dust, the temperature and other kind of properties of the dust are immersed in the optical depth of the material?
Well, I mean, so certain materials will have a certain optical depth as a function of wavelength. Right, so this is the kappa. The linear absorption coefficient is a function of wavelength. And various grains of dust will absorb more preferentially at some wavelengths than others. For instance, right? This is, I think, what you're getting at. The emission properties of that dust will also not necessarily be a pure black body. They will be a gray body or something like that, the pseudo black body, right? So we're talking in very basic terms here, and then at some point we will move into the real world and things get messy. But for the moment, all we want to do is kind of set up the formalism of this.
Okay.
Right? So we talk about things in absolutes. It's easier to think about and digest that way. Other questions? Okay. So this, let's see if we can get through the radiation transfer portion of this. So we can rewrite this equation, converting this thing and this, remember this was tau, but tau is the integral of that. And so we can consider the derivative of tau, and that's equal to this. And so we can move this over here, and this is d tau. And then we can call this emission coefficient. We can actually call this the source function. And this source function is, if it's a black body, it's going to be equal to the Planck function. But if it, right, because we're dividing kappa here, kappa goes here, and kappa goes this thing here divided by kappa. And so that quantity we showed here was equal to the Planck function if we have a black body. If we don't have a black body, then it's just the source function. And we'll leave it for later to figure out what the source function is in various cases. But for the moment, it's just a nice convenient way of framing the equation. And so we can then solve this equation again. And one way of solving this equation is by multiplying by e to the minus tau. And so if we multiply that and do the integral, we end up with something which looks like this. So we have to integrate this source function. And there's a bunch of tau primes here. This is just to sort of differentiate between things inside and outside of the integral. And so generally speaking, we have some input intensity, which is multiplied by some exponential, right? So if we didn't have a source function, this thing would disappear. And this was the original equation we had for absorption only. And so this thing is the emission portion of it. And it depends on how much radiation is being absorbed in this case. And so it depends on tau, mostly because there's a ds in here. And so if we take this integral, we can do this thing here. This thing, if we assume it passes out, we just take this integral here, and this integral ends up just being 1 minus exponent to the minus tau. I'm sort of losing my voice. It's good for you guys. Okay, so this we could rewrite this, oops, as the source function, and then this exponential, where this exponential is affecting the input radiation, but also affecting the emitted radiation, right? Because as you move through, you might emit radiation, but then later on you might absorb it back. And that's why this is a little bit more complicated. But it makes sense, I think, that you have some source function emission, which will then be absorbed, which is a function of this tau, and you have the initial emission. And at the extremes, if tau is infinite and you absorb all that radiation, right? So this thing ends up becoming 0, and it kills these off, and your output emission is just related to your source function. That's all. And this source function is as a function of the integral of ds. So this is why we can't really specify this thing a priori, because it really depends on tau. Right? And then this whole process is fundamentally related to integrating through this material. If tau is kind of halfway, we'll get some radiation from some of the earlier bits. Some of it will be absorbed, right? And so we have to compensate for that. That's why this is set up this way. Okay, so with that in mind, we can now introduce this concept, which I already kind of touched upon when we talked about the energy density inside of a sphere. And so we can think of the absorption process here as something called a mean free path. And the mean free path is the probability, or over what distance would you expect a photon to be absorbed. And so when this path, ds, times the linear absorption coefficient ends up being close to 1, then the probability of absorbing that photon is high. And so the mean free path is that distance, that distance s, more or less. Right? So if we have an average distance of a photon that's traveling through a medium without being absorbed, we have just the absorption without a source function. We have this equation here. And so we can estimate what the probability of a photon traveling at least an optical depth tau would be. And that probability is simply the exponent of this. And so the mean optical depth traveled would end up, this tau, when that's equal to 1, that's the average distance a photon travels. Right? Because this tau is a probability of being absorbed. And that's 1. That's it for the photon. So what we have to do is calculate the distance related to this tau. So this average tau is, I think this is supposed to be an average here. Let's see, let me fix that because I won't remember it if I don't do that. So this thing here, this average will, when we integrate over this and we integrate over this thing has to be 1. If the medium is homogeneous and uniform, then we can estimate a mean length that something travels, which is just given by this thing. And so this tau here ends up being equal to this times the length. And this thing here is just a form of kappa. Why there are 2 forms? Mostly it depends on who kind of developed this, because it's developed on several different several different planes at the same time. But this is an absorption coefficient, which is related to the linear absorption coefficient. And so this, we could also think of this as kappa L. This has to be equal to 1, right? And so what that means, if we move these things over, L is just equal to 1 over this alpha, or 1 divided by n times sigma squared, which is I'm both on the word now. I have to go back and look it up. And I divided it. What was that? Okay. So it's the cross section. Yeah. Okay. So it's the cross-section of the individual atoms. Yeah. Okay. So we can relate this to the number of atoms and the cross-section of individual atoms. That's all. So that's pretty easy. And so if you have this classically, the cross-section for a hydrogen atom or something like that, the number of hydrogen atoms, and that will give you the length of a photon will move before it interacts. So we have an example here. And if we think about the sun, the density of the sun in the interior is about 150 grams per cubic centimeter. If we think about this in terms of pure hydrogen, which is not exactly correct, there's helium, there's other things. But if we just assume this density comes purely from hydrogen, then we're talking about almost 10 to the 26 particles per cubic centimeter. That's a lot of particles. And so if we calculate the cross-section would be of order 1 to the minus 25, right? Because here we have number of particles and we have the length, which is related to this, how far this thing goes, and we could calculate what this thing ends up doing. But if this, well, basically the cross-section actually is this, the number of particles actually is this. And so what this means is that the average path length is about 1 millimeter. So light is emitted, it travels 1 millimeter, it gets absorbed again. It's emitted, it travels 1 millimeter, it gets absorbed again. And this is, of course, why light doesn't take 1 second to get out of the sun, but it takes 10,000 years. Right? So basically light is stuck in a massive traffic jam at the center of the sun. So we can compare this to the solar radius, which is what I did. And this process of emission and absorption, emission and absorption, emission and absorption, obviously it's going to be very rare that if you absorb a photon, it's emitted in the same direction again, right? And so every time this process happens, it's emitted in an isotropic direction, maybe, or maybe not, but it's definitely not always going in the same direction. And so this process is called a random walk, right? Which makes sense because it's going like this. Okay, so I think I'm at the end here. I'm going to stop and I'm not going to talk about black body. We'll leave that for Monday, next Monday, okay? Some of this is related to your homework using the Planck function, but we will get to that on Monday. Okay.
I have a question related to the homework. The idea is to do the homework in, I don't know, in LaTeX or something like that, and send you the document to your personal mail.
Yeah, and actually, now that I'm thinking about it, maybe it would be better to extend the homework slightly so that we talked about this with a sufficient amount of time to do it. Although I think most of you have seen black body radiation before, it shouldn't be, something new. Yeah, let me think about when I should put the deadline for the homework. But regarding the homeworks, you can do it on paper if you want, if your writing is good, right? My writing is terrible. So I'll do it in LaTeX or whatever, but yeah. So if you want to just take pictures and then do a cam scanner and create a PDF and send that, totally fine, right? No problem. Part of your homework will be graphing, and so or you can take a picture of your screen or something, but you could also just save it as something and add it as a PDF. Or you can graph it and then try to draw it. But I don't have a huge preference. Whatever is easiest, do that. But yeah, so the idea would be to send me a PDF by midnight of the due date.
I have a thought, but related with the term alpha. and kappa, because when we define the transfer equation, we use kappa like the emission coefficient, I think.
So kappa is the linear emission coefficient, and alpha is what we will call the absorption coefficient, and they are related.
Yeah.
Sometimes they are equal to each other.
Yeah, I have a
sometimes they
question
are not.
because I was reading the book,
Mhm.
and they chose the relation between alpha and kappa. Yeah, but in what case we can assume that they are equal?
Assume that they are equal until you know otherwise. We will talk about that a little bit later.
Okay.
I think that's in the next lecture. I make the distinction a little bit better.
Okay. Yeah.
Yeah.
Thank you.
So for the moment, don't stress about it too much. But we'll try and talk about it on Monday. Yeah, and I think because I didn't get to the black body yet, I will probably extend the homework to next Monday due date, and I'll send an email so it's all formal with a new PDF and everything. All right. Other preguntas? No? Okay. Good. Well, have a good weekend. I will try and do my office hours on Friday. I need to create a Zoom link within Canvas, and then you guys can do it, but it'll be a separate Zoom link from this one, I think. Yeah. Yes. Okay. Have a good day. See you guys.
Thank you.
Bye.
Bye-bye.
Goodbye.
Thank you. Bye, everybody.